Now that you've been introduced to Newton's first and second laws, let's do a couple example problems to help illustrate how to put the laws into practice. This problem is about a 4,000 kilogram spacecraft, and want to do a problem with an object in interstellar space so we can ignore any forces of gravity or air resistance and have there be just the one singular force from the thrust from the rockets. So in this case, the mass of our rocket ship is 4,000 kilograms, and it's initially traveling with a speed of 300 meters per second. So we'll say V naught is 300 meters per second, and then it travels forward and reaches a final speed of 500 meters per second. So this is still sounding like a lot of kinematics has to be put into practice. And it does so while covering a distance of 32 kilometers. So the question is, how large is that thrust? So thrust is one way of pushing or pulling, right? This is how we define force. Force is any push or pull acting on an object. In the English system, that's measured in pounds, and in the metric system, that's measured in newtons. So by asking for the thrust, we're trying to find force. Now, we're governed, of course, by this equation that says we can relate these three quantities of force, mass, and acceleration. I like to write it in this triangle. The sum of all forces is equal to the product of mass and acceleration, or we say the acceleration is the force divided by the mass, or the mass is the force divided by the acceleration. This form of the equation helps us figure out what we need to multiply or divide depending on which quantity we're solving for. So we're trying to find the force. So we need to multiply mass and acceleration together, but we're not given the acceleration. We're given the mass, and then we're given enough values that we can use some kinematics and find the acceleration. So this is a two-step process. One, find the acceleration. Two, from that, find the force. So let's figure out, we've got a displacement, an initial velocity, a final velocity, and we need acceleration. So there's no mention of time. We want to use that kinematics equation that doesn't involve time. So this is the equation v squared equals v initial squared plus 2a delta x. So when we solve for a, acceleration is equal to the final velocity squared minus the initial velocity squared divided by 2 times the displacement. So this is 500 meters per second quantity squared minus 300 meters per second squared, all divided by 2 times, we'll call it 32 times 10 to the third meters. Grab a calculator, see what you get. Okay, so the acceleration comes out to be a nice round number, 2.5 meters per second squared. From here, part 2 is pretty straightforward, right? The net force is equal to the mass multiplied by that acceleration. So 4,000 kilograms multiplied by 2.5 meters per second squared gives us what? Gives us 10,000. Well, it gives us 10,000 kilogram meters per second squared. It gives us a combination of several units. Well, there's a name to all that, right? A kilogram meter per second squared is referred to as a newton. This is Newton's laws after all, right? Yeah, so our force is 10,000 newtons. Here we've got a jet aircraft. It has some forward thrust, but at the same time, it encounters some drag forces that push back opposite the direction of motion. So we'll draw a large vector in the forward direction. So that represents 250,000 newtons of thrust. And then we'll label a backwards force of 45,000 newtons of drag. So in this case, the net force would be the difference between them, right? So 250 kilonewtons minus 45 kilonewtons gives us 205,000 newtons of net force. the plane accelerates from an initial speed of 200 meters per second to a final speed of 300 meters per second in a distance of 1 kilometer. What's the mass? So we're going to use the same kinematics equation again to find acceleration. V squared minus V initial squared over 2 delta x. So this time it's 300 squared minus 200 squared divided by 2 times 1,000 meters. Okay, what do we get this time? So this gives us, if I'm not mistaken, 25 meters per second squared. Let me double check my work. That seems kind of large. Yep, that's it. Okay, so a little more than 2.5 Gs. So maybe my picture's wrong. It's not a passenger jet aircraft. This is maybe a fighter jet or something. So not too unreasonable, but a little bit on the large side. And acceleration times mass equals force. So we're trying to solve for the mass, so we need to divide force by acceleration, which gives us 205,000 newtons divided by 25 meters per second squared. And remember, newton is just another way of saying a kilogram multiplied by a meter per second squared. So meters per second squared cancel out. We're left with kilograms. And the final answer comes out to 8,200 kilograms. A softball player slides into second base. All right, so she's running this way, goes into a dive, and then starts to skid as she approaches second base. We have her mass as 66 kilograms, and then there's a 500 Newton force of friction. Now, as she's sliding across the dirt, the ground pushes up against her just enough to offset the pull of gravity. So those cancel each other out. And although she has a velocity in the forward direction, there's no force propelling her in the forward direction. In fact, the force points back in the negative direction, and that's this force of 500 newtons, okay? So a friction force of 500 newtons pointing opposite the initial velocity vector causes her to decelerate and skid to a stop as she reaches the plate. So the initial velocity is 9 meters per second, and we assume that the final velocity is equal to 0. So we got to figure out how far she was from the plate when she started sliding. So what's that distance? So, gosh, if we were just to try kinematics, see, trying to find a distance, we have an initial velocity, we have a final velocity, and that's it. Well, there's not enough information to choose any appropriate kinematics equation. If only we knew acceleration, then again, we could use the same kinematics equation we've used in every one of these example problems. V squared equals V initial squared plus 2a delta x. So delta x is final velocity squared minus initial velocity squared over 2 times the acceleration. But we can get the acceleration as long as we divide the net force by the mass. So we divide the force of 500 newtons by a mass of 66 kilograms, and we get about 7.58 meters per second squared. Although I believe that's negative, right? We're going to make a frame of reference where positive motion is to the right. So the initial velocity is positive 9 meters per second, but this force is actually a force of negative 500 newtons. And so we have an acceleration of negative 7.58. So when we plug everything in, 0 minus positive 9 squared divided by 2 times negative 7.58, the negatives will cancel out. And we get a final answer, delta x, of 5.34 meters. Okay, so there you have it. A couple quick examples of applying the formula, either net force equals mass times acceleration equals net force divided by mass, or mass is equal to net force divided by acceleration. Okay, all three of them, all three forms of that Newton's second law equation can be seen if we write it in the form of this triangle. And of course, we can't disregard our understanding of kinematics as we proceed through the material.